I'm very happy to be here. My name is Miran Ceh. I'm coming from the Jozef Stefan Institute in Ljubljana, Slovenia. And I would like to give you some recent results that we did on oxide thermoelectric materials. This work has been also done in collaboration with our colleagues from Turkey, from the Sabancı University, and also from Germany. A brief outline. So why do we do that? Because I always like to have a little bit more comprehensive story. Something about growth planar faults in the perovskite materials, which we used in order to tailor some thermoelectric properties. And then I will focus on the results on strontium, titanium, niobate thermoelectric materials, and short conclusion. So thermoelectric materials are of course important because they actually can turn the thermal gradient into electric output. And there are some thermoelectric generators already present, of course, on the market, which are composed on the P and N type. And then, of course, we have some thermal gradient across. And composing those into thermoelectric modules, we can get some kind of power out of that. So there are a lot of materials, and we specialize in oxide materials. Some are P types, some are N types. So this is like strontium titanate, which is doped with niobium. But there are extremely high values of so-called ZT factor for some layered nanostructures. So how to define the quality of this type of materials? We describe them with a so-called figure of merit, ZT, which has three components really. Well, also depends on the temperature. One is the Seebeck coefficient. The other one is electrical conductivity, which of course is a little bit complicated because as soon as you increase the charge carriers, then of course the Seebeck coefficient goes down, so there is some optimum concentration of carriers and also a Seebeck coefficient that allows you to have a relatively high electrical conductivity. And finally there is a thermal conductivity term, and we have to distinguish between two contributions. One is actually retained with the lattice and the other one with the electrons. Nevertheless, all these parameters are strongly correlated, and especially this one. If we talk about oxide materials, then the major contribution in oxide-based material is actually the phonon scattering. Okay, and if we talk about other materials, of course, we're talking about electron transport. So, how to improve the ZT value? Okay, there have been many tries really to do some engineering in the microstructure of these polycrystalline materials, such as grain boundary engineering, some inclusions, some superstructures, so that we have some layered structures. And what we decided to use is try to implement so-called planar faults into the microstructure. With this, we wanted to increase the phonon scattering, hence reducing the thermal conductivity and consequently, of course, to increase the ZT of the material. So we know quite a lot of these planar faults in perovskites because we have been doing that for many years now, especially in this perovskite structure, which is also strontium titanate based. If we dope it with niobium, then it's also a perovskite structure. So if we dope this material with AO excess, we get so-called Radles-Dampopper type faults or phases. So we have a perovskite structure here and here, and then there is some kind of a shift in half of 110 direction. In, let's say, another projection, this looks like this. So we have a perovskite, and we have an interleaved layer of strontium oxide. So there are a lot of, well, there are actually only three stable phases, so-called Radles-Dampopper type polytypic phases. So let's say we have only one perovskite layer, which is interleaved with single strontium layer, 2 layers perovskites, and 3 layers. What happens if we add actually the strontium oxide into this material? Well, first of all, we get anisotropic grain growth, and then we have some planar faults which are either ordered or disordered. And we have done a lot of extensive studies in high resolution TEM, also trying to see the deformation of the perovskite lattice adjacent to these planar faults. We were also calculating these distortions we found out that, of course, there is some distortions in the first perovskite layers adjacent to the faults. We have done a lot of annual dark field imaging, annual bright field imaging, and these state-of-the-art CS-corrected microscopes, which are available nowadays. So we were pretty sure that by introducing those faults, we could probably influence the microstructure and the final ZT value. A few more data about the strontium titanium niobate basic phase. I would say it's a perovskite, solid solution with niobium. We also have different ZT values. So the highest ZT value of so far explored materials is at 2 atomic percent on the B side. And then, however, high thermal conductivity is something that hinders the thermoelectric properties. So if we put niobium into titanium position into this oxide perovskite structure, and we are dealing with the oxygen-free atmosphere, then we get some reduced titanium also, so some vacancies which affirm or confirm that we have a sufficient high electrical conductivity. And as I said, there are some epitaxial films as compared to dense ceramics, which have, of course, higher figure of merit ZT. So what was our idea? So we have a stoichiometric polycrystalline material, and then we can add this type of faults in two ways, either as some seeded materials, also to induce textured microceramics or microstructure, and the other is simply to add strontium and calcium oxide. So I will just talk about this at this point. Microscopy, of course, was a crucial analytical tool that we used into evaluation our results as well, apart from the thermoelectric measurements. So we see that when we add strontium oxide, we get some polytypic regions which are ordered and maybe some 3D randomly orientated RP faults in the microstructure. Nevertheless, we do introduce some of the anisotropic grain growth. If we go to high resolution, we see that there are some regions with those ordered faults, and this is a pure perovskite matrix. And this high resolution image sees that there is a single individual planar fault, and there are like 5 unit cells in between that. Okay. So the question now arises also, how is the niobium distributed on the B sides? Because niobium is the one that assures the, I would say, the correct electrical conductivity, and this we did with quantitative high-angle annular dark field imaging. I will not really go into detail. What is this is, so this is the mixed titanium and niobium on the B side, and this is like strontiums. And if you take the experimental profile across those titanium mixed columns, you see which are here red ones. We see that there is a lot of scatter. That means that the concentration of titanium and niobium on B side actually is not very evenly distributed within the single atom columns. So we did some calculations, imaging simulations to see how the concentration or the intensity ratio between A and B side would be in case if we were increasing the niobium content. And we found out that in our material, this is the measured ratios, and this is converged to the compositions on the B side. We see that, of course, the titanium and niobium content, especially the niobium content on the B side, is varying somehow between 5 or 30.35 in this strontium titanium niobate. So this is important in order to retain electrical conductivity. This is also a high resolution EDS mapping. It's very tedious to do that on such an atom level, even in a CS-corrected microscope. Nevertheless, this is the fault here, and these are 1, 2, 3, 4, 5, 6, 7 strontium atoms, and this one, which is titanium position, you can see that between this and this is like 3.8 angstroms. So we see that the intensity of niobium and titanium here is a little bit in a correlation as compared to the other ones. So this atom column has definitely less niobium and higher amount of titanium as the other ones. So pretty similar if we put on calcium oxide. However, since calcium oxide is smaller than strontium, it actually forms a lot of loops, three-dimensional loops, like here, which means that we have really 3D orientation of these planar faults. Again, with the STEM imaging, we could identify this is the strontium and calcium mixed columns, and we were interesting if also calcium goes to the preferentially into the matrix or along the fault. So we did a spatial difference analysis using EDS, also with EELS, and we can actually see that at the fault we have a larger concentration of calcium, which makes sense because it is a little bit smaller compared to strontium. So that was our main idea. So we have to substantiate that with the thermoelectric measurements. And what happened in both cases is this is either strontium oxide or calcium oxide doped, and this is pure strontium titanium niobate. The thermal conductivity actually was lower. The one that is actually contains to the phonon is also lower, and in this way we managed to increase the ZT value of dope material with calcium oxide, not with strontium, because the electrical conductivity was a little lower, but in principle we were quite happy that by doing this, by incorporating some nanostructure features into the microstructure of this perovskite material, we were able to increase the final ZT value. So this is in very short, just a little bit of conclusion. Of course, microscopy is extremely important in any atom-resolved characterization, either structural or chemical, of any materials. So when we add those strontium oxide and calcium, we formed like polytypoitic sequences or isolated faults. Also, the concentration of titanium and niobium was different on the B sides, and this approach to incorporate this type of faults into the matrix turned out to be beneficial, so that we were able to increase the figure of merit or ZT of the materials. Okay, thank you very much for your attention.